then I'm gonna show the reminder, you know, every time. So let me do this. Share the screen. So I think today is May 19th. Okay. I believe right now we have around 10 presentations left. So it probably would be today and also Thursday. So Thursday would be our last class. Okay. And then today by midnight, the textual program, which the due date was extended for 1 week, which is today, would due on today midnight. And then there's another last written assignment, okay, which has been posted since last week, and the due date is Thursday midnight. So by Thursday midnight, okay, everything is drop dead date, meaning that I need to start grading and then tabulate and calculate the whole grade. And don't rely on the grade on Moodle, because the Moodle, the way it's set up, it has some sort of an equal distribution by whatever the software default configuration. I think the weight of each of those activities, like the quiz and the homework and all those, as listed on our first lecture, okay, that I have slightly distribution in terms of the weight of each of those activities, okay, because I got an email asking me about a certain weight on let's say presentation, okay. So so I think don't depend on whatever the grade on Moodle. The final grade will be posted on board system, okay. So I hope that I will finish all the grading by this weekend, and then as soon as I finish, if the system open, then I will post all the grades on board system. Then you can later on check it, okay. So let me just show you the presentation roster right now. I think we are up to number 24. The next is 25 or 25th, which is Najera. So it's Najera. Are you ready? If you're ready, go ahead and speak up, and then I'm gonna unshare my screen, and then we can get started.
Yes, Dr. Box, I'm
okay.
ready.
All right, let me just stop my screen sharing, and then right after that, then you can start sharing yours. Stop screen sharing. Okay. Okay, go ahead. And once you have everything ready, I will mute and also stop my video so that it would not occupy any bandwidth.
Okay. Are you able to see my presentation?
Yes, I do. Okay, go ahead. Go right ahead. Okay, I'm gonna stop my video and mute. And everyone, please mute your microphone so that whatever the background noise would not interfere with presentation.
Good morning, everyone. My name is Nirjala Parajali, and today I'm going to be talking about Unix or Linux boot up process. Let me ask you a simple question today. Have you ever wondered what happens behind the scenes from time to time when you press the button until the Linux login prompt appears? If yes, these are the few steps that are involved as soon as the startup process is enabled. BIOS is the first step after powering on your device. The basic input-output system initializes the hardware, including the screen and keyboard, and tests the main memory. This process is also called post-power on self-test. The BIOS software is stored on a ROM chip on the motherboard. After this, the remainder of the boot process is completely controlled by the operating system. master boot records and bootloader. Once the post is completed, the system control passes from the BIOS to the bootloader. The bootloader is usually stored on one of the hard disks in the system, either in the boot sector, and that is for traditional BIOS MBR systems. Up to this stage, the machine does not access any mass storage media. Thereafter, information on the date, time, and the most important peripherals are loaded from the CMOS values, which allows the system to keep track of the date and time even when it is powered off. A number of bootloaders exist for Linux. The most common ones are Grub. Most Linux bootloaders can present a user interface for choosing alternative options for booting Linux and even other operating systems that might be installed. When booting Linux, the bootloader is responsible for loading the kernel image and the initial RAM disk into the memory. There's another bootloader in action, Grub, which I'm going to talk about right now. This has two steps, and in the first stage, for most systems using the BIOS MBR method, the bootloader resides at the first sector of the hard disk, also known as the master boot record. The size of the MBR is just 512 bytes. In this stage, the bootloader examines the partition table and finds a bootable partition. Once it finds a bootable partition, it then searches for second stage bootloader. For instance, it could be anything like Grub, and loads it into the memory, random access memory. In the second stage, the bootloader resides under root boot, and a splash screen is displayed, which allows the users to choose which operating system to boot. After choosing the OS, the bootloader loads the kernel of the selected operating system into RAM and passes control to it. The bootloader loads the selected image and passes, after passing the control to it, kernels are almost always compressed. So its first job is to uncompress itself. After this, it will check and analyze the system hardware and initialize any hardware device that drivers built into the kernel. Next, I'm going to be talking about the Linux kernel. The bootloader loads both the kernel and initial RAM-based file system into memory so that it can be used directly by the kernel. When the kernel is loaded in the RAM, it immediately initializes and configures the computer's memory and also configures all the hardware attached to the system. This includes all the processors, input-output subsystems, storage devices, and so on. The kernel also loads some necessary user space applications. This is a picture of your usual initial RAM disk. This file system image contains programs and binary files that perform all actions needed to mount the proper root file system, like providing kernel functionality for the needed file system and device drivers, for mass number of storage controllers with a facility called UDAVE, which is for user device, and that is responsible for figuring out which devices are present, locating the drivers they need to operate properly, and loading them. After the root file system has been found, it is checked for errors, and then after that, it is mounted. The mount program instructs the operating system that a file system is ready for use, and it associates it with a particular point in the overall hierarchy of the file system. If this is successful, the initial RAM disk is intra-MFs is cleared from RAM, and the init program on the root file system is executed. It handles the mounting and pivoting over the final real root file system. It also, if special hardware drivers are needed before the mass storage, it can be accessed, and they must be present in the intra-MF's image. Now I'm going to be talking about init or SVN services. It usually starts other process to get the system running at the end. Once the kernel has set up all its hardware and mounted the root system, the kernel runs init program. This then becomes the initial process, which starts the other processes to get the system running. Most other processes on the system trace their origin ultimately to the init. The exceptions are kernel processes, and it is started by the kernel directly for managing internal operating system details. Text mode login. Near the end of the boot process, init starts a number of text mode login prompts, which I'm sure everyone has seen. This is done by Getty. This enables you to type your full username followed by your password and then eventually get to command shell. Usually the default command shell is bash, but there are a number of other advanced command shells that are available. The shell prints a text prompt indicating that it is ready to accept commands, and after that the user types the command and presses enter. The command is executed after this, and another prompt is displayed after the command is done. Windows system. Generally, in a Linux desktop system, the X Windows system is located as the final step in the boot process. A service called the Display Manager keeps the track of displays being provided and loads the X server. So it is so called because it provides graphical services to application, and sometimes they're called X clients. The Display Manager also handles graphical logins and starts the appropriate desktop environment that a user would see after he logs in. Here are some references if you're interested, and that's my presentation. If you have any question, please let me know. Thank you so much.
Anyone has any question? Especially, I forgot, I think we have one guy was presenting this booting mechanism as well.
Yeah, I think I've seen this presentation.
Najira, can you go back to probably second slide, that 7 steps or 7 or 8 step that you had?
Yeah.
Okay, all right, this is 8 step. I mean, your presentation is very Linux centric, okay? What if, you know, I mean, I want everyone to kind of get a picture or idea. Which of these steps are Linux centric? Which of these steps are, you know, operating system agnostic, meaning that it based on whatever the hardware mechanism, and from which state there would be particularly like operating system centric, like Linux centric, or we can change or replace that Linux with Windows, because I believe that, you know, I mean, to start, or
it's in the BIOS, I believe. It is the one that initializes the hardware.
Mm-hmm. And up until what? Up until what? Which is not operating system specific.
Sorry?
Which are the steps that not operating system specific? Because your presentation is really Linux centric, right? And I want everyone to start seeing, you know, I mean, which of those steps are not operating system specific, which are those steps are operating system specific.
This is pretty much almost the same with Windows and Linux, and as to where the road for Windows and Linux separates, I think, according to my knowledge, I think it would be as soon as we initialize the hardware in BIOS, but I'm confused. I'm really confused about it.
Well, I think it starts from grub. If you look at the grub, okay, grub or Lilo, you can use either grub or Lilo. There are two most popular kind of unified booting mechanism, okay, which is, I think we didn't touch a whole lot of BIOS because it's a hardware thing. But I think chapter 2, we talk about bootloader or whatever bootstrap kind of mechanism, okay, which point to whatever the master booting, and then later on it start pointing to the image, okay. Now the graph is a tools that being introduced probably 20 years ago that allow multi-boot, because if you want to have a menu that would show you the choices of whether you want to, I mean, normally you have a default operating system that it's gonna start, kick off whatever the image of a target OS and boot. But then, like 20 something years ago, some of these mechanisms like Grab or Lilo has introduced menu in a way that is not, it's a partially like hardware and also software, but not operating system specific. And then you can choose the choice of whether you want to boot from Windows, Linux, or whatnot, So
I think that's typically in the second stage that happens in the grub. I have mentioned that in.
no, the grab is third step from your presentation.
Oh yeah, in my presentation it's grub is the third stage, but if you remember I said there are two stages involved inside that's first stage and second stage. And I mentioned that you would be able to choose your operating system from the second stage inside the grub, but whenever you asked me the question, I thought you were referring to how the system chooses in there and not according to the user. So I was kind of confused.
Okay. All right. Let's go to the graph. Then go to the graph slides.
Okay.
Looking into this graph slides. Okay. This is again. This is a starting place where you can be a operating system specific, okay? Because you can see that you can boot off that CentOS, which is one of distribution. If you want to boot off from different others Linux like Ubuntu or whatnot, those are the starting point where later on you have the root, the kernel, whatever those image, okay, and then the initial kind of the boot record kind of things, okay. So I think this is in fact the screen or the step in which you can swap out any type of operating system, start from here. And in fact, if you want to have the splash screen, which is your girlfriend picture or boyfriend picture, you can replace with that splash image, okay, which is on the fourth line there. Okay. So I just want to point out. And then the last comment, not just for you, but for everyone also, go to the RAM disk.
Okay.
Yes. You didn't draw this picture, right?
I extracted it from, it's from edX, and I have properly referenced it at the end.
I think you can reference on the back, but anytime when you do presentation, if you have picture anywhere that appear, underneath that picture, it should quote the source, okay? That is an ethical way that, not just you, for everyone, okay? Because otherwise, I mean, you should not just you, we should not have our own convenience to say, okay, go and find out the reference, on the back. I think we should acknowledge the author, who has come up with, this material or their own diagram, acknowledge whatever the source or the original author there. It's not just for you, Najira, this is for everyone. So whenever you have the picture, don't say that, oh, I have references. No, I think that's, for me, who've been in this industry very long and also in as well as academic, it's always nice to just quote right there, okay, underneath whatever the picture or the code that you take from somewhere else. Okay, all right. That's it. Anyone has any question? If not, yes, go ahead, Nijara. Okay, you can unshare the screen, and then let me see who is next. Next is Chris McKay. AI in compiler. Are you here, Chris?
Yes, I'm here.
Okay, all right, go ahead and share your screen, and once I see everything, then I will stop my video and shut up. Say
All
something.
right.
Okay, I think you're good to go.
Good. All right. Awesome. So like you said, we're going to talk about the role of AI in compilers and how machine learning has helped to improve on technology, make them faster, and just kind of improve the overall performance of our different machines. These compilers work on all operating systems. They work on pretty much any device that has a CPU, RAM, and all that kind of stuff. It pretty much works on everything. So just to give you an idea of what we're going to talk about, we're going to talk about the journey to compilers and the different technologies that they had to work with before we had compilation techniques. Then we'll show the advanced techniques that they're using in compilation that help to improve system performance and give us some energy efficiency and things like that. And then at the end, we'll give the future of compilers and what challenges they're facing when they're improving them and using this this machine learning to make things better, and where we can go from there. So to start off, machine code to compilers. So before, everything was done in machine language, and this was kind of a downside because you had to hard code each individual instruction that the CPU was handling, and it was really time consuming just to do simple tasks. And so it really was not an easy time for these programmers to do anything with their computers. And so that's when they came out with assemblers, which allowed them to map these individual instructions to commands. And so it allowed them to speed up their coding, made it more simplistic and easier to read for people that weren't quite as familiar with programming. Then they came out with a macro assembler, which was even more simple. And this was the introduction of the if-else statement, so it made it even more easy to read. You could do variable declarations. So in this case, you could do int I equals 0. Before this, you couldn't really do that. It was more difficult to set something equal to something in a simple way. Then after that, we had our high-level languages that we know today. So they started out with C and BASIC. C is probably the most popular one that is still used today. It gave more flexibility, easier to read variable declarations, easy to use loops and if statements. You could have multiple statements on each line. And so it was just much easier to read and understand. But the downside was that translating from these high-level languages required new hardware and new software, because it was much more difficult to translate from these high-level languages to machine code than it was to take it from an assembler and put that into machine code. So that's when they came out with compilers, and the most popular, the first popular open source compiler is GCC, which I actually use that to compile my C programs today. It's open source, which means it's free to everyone. You just have to download it in your Linux terminal, and you can use it to compile most of your high-level languages and architectures, and it just makes compiling much, much easier. And so now people just call their compilers from their Linux terminal, and it allows them to compile any of their programs easy. So much easier than having to do the machine code a long time ago.
Hey, Chris.
So, yes?
Quick things, bring back a lot of memories, whatever your presentation here, because, you know, I mean, when I studied, we went through all those things. In fact, I think period of my past experience, I also research into compiler. So do we have any class that you guys had assembly or macro assembly in those classes in at Louisiana Tech? Because I didn't graduate here and I don't teach that class, and I can't tell.
Yeah. Well, I'm currently in computer architecture 364. And we've done a little bit of assembly. We've done x86 assembly, and then we've done MIPS assembly.
Okay, I see.
So,
Do you also have a macro assembly, which is a higher level than that hardware assembly?
I personally have not used a macro assembler. I've used the simple assemblers,
Okay.
but
I see. Okay, which is I think it's still good, even though no one program is assembly at all, but it gives you some idea how each level works, so that if you want to deep dive into that level, I mean you can do so, because somehow someone or the two responsible at that level, even though it's being hidden for the developer nowadays, that most of you guys program in high level language, just like C or C#, or even interpreter like the Python, Ruby on Rails, or whatnot. Okay. All right, go ahead, go right on.
All right. So then after that, they started to develop better compilation techniques. These are a few of the techniques that I'll go over more in detail. But like I said, all of these techniques help to improve efficiency, reduce runtime, and just kind of make things faster. So the first one is parallelism, and this is a way of finding patterns in your code.
Watch out, Chris. This is all my areas, all my previous areas.
Yeah. So the parallelism, it finds patterns in your code and creates the instruction set for that pattern before you even execute your program. And so that really saves on runtime, because most of the hard work is done before you hit the run button. And so it really saves on the runtime. It generally will choose a different data structure than what you actually input, because sometimes people put in data structures that aren't super efficient. And so it uses machine learning to figure out the best data structure to put your data in, so that when it turns it into machine code, when it translates it to assembly code, then machine code, that is a very quick process. And then it also uses a process called synthesis, which creates a sub-program that generalizes most of the data that's in your program. And it kind of also reads that sub-program with the generalized data, which helps it to kind of learn what you are intending with your program. So
the good candidate for data structure or code block that can be parallelized, array or vector, and then the loop, the iteration. Some of those can be transformed into I think one type of parallelism called data parallelism, where you can just execute one operation but based on all the data there. And right now, type of hardware such as GPU or some built-in vector processor that may be in the current processor there. Yeah, good. It's bringing back a lot of my memories.
I'm glad. Hopefully they're good memories.
Yes.
So then the next technique that they use is reduce in strength, which means that they simplify a lot of complex operations that we use in our different functions. So for example, x times 2 is using multiplication, but unfortunately, computers take a long time to process multiplication and division. And so if we can turn those multiplication, division, complex operations into just addition and subtraction, that really increases our it slows down runtime and increases the number of processes that can be done in a certain amount of time. And so that really reduces the number of operations that are needed. It kind of simplifies loops as well. And so it doesn't have to spend as long on those loops. And then this reduce in strength also helps to make the translation from high-level code to assembly much easier. And then obviously from assembly to machine code, because assembly code is pretty close to machine code already, the translation from assembly to machine code is decently fast. So if they can make a fast translation from that high-level code to the assembly code, then your runtime is going to be much, much faster. So that's that's another way that they reduce runtime. And so the next one is approximate computing. Now this is kind of a controversial method because it gives up a lot of accuracy on your data, but because it does the approximate computing and it's not as accurate as possible, it really improves on power efficiency. And this is mostly dealing with mobile devices that use small lithium-ion batteries. If we can reduce the amount of time that it's calculating this data by giving up a little bit of accuracy, then that really helps to improve that power efficiency. It is difficult to program, so that's why the process of improving power efficiency has taken so long. Smartphones have been out for quite a while now, but smartphones are really just now starting to kind of find their way into really much more power efficiency. And that's because it's such a difficult way to program. It's also used in big data analytics, on augmented reality and web searching. The approximate computing really helps to kind of make predictions and kind of give these analysts an idea of what would happen with certain data that they put in. And so that helps them to kind of not only make predictions, but also make these applications for augmented reality and web searching a lot faster. And then it takes a lot of advantages of soft errors in many mobile applications. And this, again, allows it to be much faster on mobile devices. So, and then the last one is code motion. And this is a process of moving most statements and expressions outside of loops, whether it be iterations or recursion, without affecting the output of the code. So this is a lot of variables and expressions that don't change. And so if they don't change, they don't really need to be inside the loop. And so these compilers can move those outside of the loop so that it can focus on the changing variables, use its resources on that, and that definitely improves runtime and allows the compiler to be more accurate because it's focusing on those changing variables instead of the constants that aren't changing. It avoids redundant computation. So, if you're not having to continually make instructions for these expressions and variables that don't change, then you can really reduce the amount of processes that are needed. It reduces code size that and that would be the machine code after it's been translated. And then it also saves on CPU resources, so it doesn't have to use as many of your cores whenever it's compiling, and it doesn't have to use as many threads either. So that is CodeMotion. And so just to wrap things up, compilers have come a long way. We've come even further from having to do everything in machine code to now we can, have for loops and if statements, and we can use recursion and all of those things. And so that all of that is because we've made so many improvements to our compilers. And so just some future looks and challenges at our compilers. The transformation from high-level code to assembly/machine code still needs optimization. That's where we can really see the runtime affected. If we can continue to optimize that, then our computers will be so much faster in 10 years. These optimizations that they've made already, though, continue to improve system performance and runtime. The smart compilation techniques that they have been using is the key to power efficiency for all our mobile devices. So hopefully our mobile devices will start to last all day long without any trouble. And they still have to balance accuracy of these calculations with performance, because like I said, the approximate computing they use in these mobile devices is pretty controversial because the data isn't as accurate as possible, but then again, it does give you better battery life. So most people say that that's a trade-off that they're willing to make. So, and then here are my references. So that's everything that I have. So if there are any questions, please let me know.
Any question for Chris? A few comments, Chris. I just want to share my experience with all of us here. I'll point out to something that obvious to you, and then something that we also touch upon in the class. I mean, for example, the compiler would generate the code, and the code will run on the runtime or execute, and then the execution would be handled by operating system. So you can see the connection from there. So a lot of time, I believe that, the future of smart compiler or this AI compiler has to have some relationship or connection to the compiler, the runtime, and also the OS aspect in order to collect data, because the AI would not work by itself. It needs to start looking at the data, training, based on the data that get collected. Okay, so I think that that's something that I want to point out, so that you start seeing the connection from whatever Chris present all the way to compiler aspect. Okay. Also, Chris, I mean, can you go back to the CodeMotion? I just want to give some example. You all remember when we talk about function call, right? The process has to manage those the function calls by push and pop the stack. Then pushing and popping from the stack is the activation record that it remember what's the caller and what the callee, so that it can come right back where the calling point call to those function. Okay. Now with the function calls, the activation record has to be created. Okay, so therefore there would be an extra overhead, call those function. Okay, what if that function that perform one instruction, just like A equal to B plus C? Wouldn't it be faster if you just embedded B plus C into those functions instead of make a function call? Because if you make the function call, the runtime has to create activation record, push that activation record onto the stack, and then transition into those statements, execute the statement A equal to B plus C, and then after it's done, then it pass the result back and then pop the stack. So you can see that a lot of overhead there, where if someone just trying to write the code and then sometimes unnecessary to do the function call. I don't say that don't do the function call, but sometimes if you want to optimize your code, then in terms of code motion, when you start seeing function call, okay, then you can translate those function calls, especially recursion, into we call loop roaring, okay, LOPP, like loop, and then roll the loop, so that it will mimic the way the recursion or the function call recursion take place. Okay, for example, if you guys familiar with, you guys take data structure and learn Fibonacci function, or some of those that you can call by based on the recursion, which is quite simple and powerful concept. But then in terms of the runtime, it may add additional overhead where the function call get called by pushing and popping the stack. Does it make sense? Does it make sense to you?
Yeah, of course.
Yes. So I think that's what I'm trying to point out, what we learned from the class and whatever Chris kind of mentioned. I mean, different techniques that how people do optimization. It kind of bring my bells, bring back a lot of memories that I did some optimization in the past, and the work that it make my name. I think a lot of us, you guys don't know my background. I work a whole lot of supercomputing, with NSA, with Department of Defense, with Department of Energy, that I cannot, announce or advertise. Sometimes some project I have to keep my mouth shut. I mean, so I mean, right now I'm no longer work on those, and I'm not gonna touch into more detail. But I can tell you that whatever Chris present today, I would say that you will see more and more in the future, because if you look at your programming aspect, you're gonna write A equal to B plus C. You're gonna declare your variable to be here and there, like an array or 1, 2, 3 dimension. You don't actually declare any hardware specific, but now your hardware start getting sophisticated. You have both CPU and GPU mixed between two. You also, I mean, having like quantum computing coming to the next generation. So in that case, compiler would play a significant role to translate your high level language, which is hardware agnostic, into hardware optimization. If that thing makes sense to everyone, so that's what I foreseen some of these things coming in near future. And this could be some of you guys career too. In fact, every week I speak to my student, last PhD student that I try to push. We just talk about AI. We talk about optimized AI with the GPU or cluster of GPU or GPU of GPU. I mean, if you follow NVIDIA just announced the latest GPU core is called Ampere, that they can create 7 instances of GPU card within one GPU card, so something coming, something coming along, some excitement that gonna push envelope and propel all this computing technology into next generation. And therefore compiler and languages would be one of the most important aspects for us, for all of us who are in computer science or cyber engineer, that will make use of and then distinguish ourselves from the regular user. I think that's why I really appreciate what Chris kind of present today, because it just remind me about good memory in the past too, as well as what I think in the future. And last but not least, for GCC that Chris mentioned, you can use -O as optimization option, so. All right, anyone has any question for Chris? If not, let's go to the next person. Thank you, Chris.
Yeah, of course.
Kevin, artist. Okay, is Kevin here? You're gonna present on cloud computing.
Yes, I'm here.
Okay, go ahead, do the setup, Kevin. And once you're ready, I would acknowledge and shut up and then turn off my video. This is also my field. All right, go ahead. Speak up a bit, and then before I mute my microphone.
Okay, I'm just trying to. So can y'all see that?
Yes. Okay. Go right ahead, Kevin.
Okay, so I did mine on cloud computing. I'm Kevin Ortiz, and whether we realize it or not, everybody uses cloud computing. Like we might not like see it as so, but I'm pretty sure all of us do. But some people don't realize that almost everything they're using on the internet is in terms connected to cloud computing. And cloud computing is simply the delivery of computing services across the internet. And so that's really cool about cloud computing is that it replaces oftentimes it replaces the need of you to actually having to physically upgrade your hardware on the computer because you're pretty much borrowing like the hardware that people like other like services other companies provide. And this allows for a lot of flexibility with computer resources. And since you don't have to worry about physically maintaining the hardware, it often makes it easier on you or like customers. And there's a big reliability factor. At the same time, there's not, because if you're like using a prominent company that are known for properly maintaining their hardware, like you can pretty much be assured that like you have copies of all your information at various locations. But if you're not using like if you're using just a company that's maybe like barely starting or like they're known for not really keeping up with their hardware as well, there might be an issue with data loss. So there's various types of cloud computing, and well, there's three types of cloud computing, and those are public, private, and hybrid clouds. Now, public clouds are typically run by third-party providers because this is the one that pretty much everybody comes across, everybody uses, and they provide resources such as servers or storage and their access to web browsers, obviously. While private clouds are used for a group of people, for like a specific group of people, like let's say like a company, organization, or something, a business, and they are typically located like in the same building, like um in the same building because it stores all the company's information, all the organization's data, everything they need. But they could be provided by a third party too. It's not necessarily in the same place. Now, hybrid clouds are pretty much what it says. They're a combination of the two. A hybrid cloud could provide like services for just the general public, or they could provide specific ones for organizations. And they're a lot more useful because it allows for the possibility of, like, let's say a private cloud, like people that are using a private cloud and they want to share some of their data, they can easily just allow it, like they can pretty much just I can't think of the word. So they can pretty much, like, they're already technically under the same cloud, so they can pretty much just show it to the public instead of having to maybe grab all the data and having to upload it. And this gives a lot of flexibility. Now, there's different types of cloud services, and they all fall under these 4 categories, which is infrastructure as a service, platform as a service, serverless, and software as a service. Now, infrastructure as a service is pretty much the most basic, and we all use this. well, I think I double clicked. Yeah. Infrastructure as a service is the most basic, and we all use this because we all store data online, like Google Drive or let's say OneDrive from Windows, and it's pretty much just the renting of IT structure, or maybe not even renting, like Google Drive, but none of us have to actually pay for that. But if we do want like a lot of times there are options to pretty much have more storage online for certain services. And pretty much it doesn't have to be like storage. It can be servers, VMs, networks, or OS. Now, the next one is platform as a service. Now, this one is used more for developers and for people that are like working on applications or working on like just different softwares. And because this is used for developing, testing, and delivering. And this is pretty much for developers to easily work on their applications or work on their things without having to worry about like, making a server, like having to like physically like, set up a server so that they can test all their things on. They just use these platforms as a service so that all they have to worry about is the application. Now, serverless computing though is similar, but the thing is it allows for like you don't have to like set up like with platform as a service, you might still have to allocate like how the server works or how the network is. But with serverless computing, all that is pretty much scalable already. So it's a lot more focused and it's a lot more flexible. But like you might want to be in charge of controlling all that. So that's why there's two different ones. Now,
Kevin,
yes.
do you think that the serverless computing is somewhat similar idea or concept that container or whatever Docker or Kubernetes provide? I mean, I'm not sure you listened to I think a few talk in the past that people talk about, the Kubernetes or the Docker or the container. Because I know that this is a generic term, but the Docker and all those are a concept that people, the Docker is implementation of the concept of container. It sounds like, in terms of functionality, you just focus on building your application, not worried about the configuration or things like that. It seems like the serverless computing, in terms of the end user, it gives the same kind of idea or concept, that the Docker or Kubernetes provide. So do you agree, or someone who has present, I forgot the name, Kubernetes or the Docker, do you see similar thing that the serverless computing provide?
Yeah, they do seem similar. Like I didn't personally like look into the Dockers, but
Mm-hmm.
from the sound of it, they do seem like pretty similar.
Yeah. So okay, all right, maybe you can move on, but whoever present Docker or Kubernetes, you can chime in or put in the chat room as well, so everyone can see your opinion. I just want to spur or encourage participation or Q&A, so that it would be more lively presentation, not just like listening. Somehow interaction, I think it would promote more creativity or some idea that we can connect further. Okay. Yeah. All right. Go ahead, Kevin.
So lastly, there's software as a service. Now, this is actually just using like applications that are used over the internet, and you don't have to like the same thing applies. Like you don't have to worry about like any of the infrastructure. You don't have to worry about hardware maintenance or even the software this time, because all this is provided by another another organization, another party. So, and this thing includes like things like email, Skype, and all that. Now, something important to know about cloud computing is that it has rapidly grown a lot since first introduced, and now it's pretty much used by everybody in our daily lives. Like such, one of the reasons we're able to keep up with our online classes, even though like the whole virus, because we can stay connected and we can stay we can keep on everything online. And as I've been mentioning, cloud computing is seen everywhere nowadays, and it's used from just individuals, from our daily lives, from just like our what we need for school, to like global corporations that store all their data and information. And these are my references.
Any question for Kevin? I just did a quick Google on servlet computing and container. Yeah, I think it's similar in the nature, but it says that container is probably allow you to customize the configuration more than servlet, you know. But in terms of the end user, because they said that because of the servlet function are smaller than container microservices and do not come bundled with system dependencies, you know. So, well, I think like Kevin said, the cloud computing, it become very important. I think it's important enough that 5-6 years ago, I give up one of my career subject, which is supercomputing or high performance computing, that I teach you guys to program multi-cores, the GPU and all those, and switch to cloud computing 5 years ago and start cloud computing, distribute and cloud computing class at Louisiana Tech first time. And I think some of you guys know that 2-3 years ago, I went to Asia as a dean, and I give up that class, and now Ben, Ben D, Professor Ben Drangos, I think he's teaching that class. So we have this class available, but I don't know how he teach that one. I would say that if you have option of the elective class, take that class, you know. Besides AI, I think AI is important. Cloud computing also as well important, okay? All right, okay, Kevin, anyone has any question for Kevin? Otherwise, we go to the next person, which is Evan Sumwalt. Yes, go ahead, set up Evan, and I will mute the microphone after you finish setting up.
Can you all see it all right?
Yes, I can see and I can hear. All right, go right ahead.
Okay, my presentation is going to be on Docker, which is an open source development tool. And I'm going to cover what Docker is, a little bit of history behind Docker, how it works, an overview of what containers are, containers versus virtual machines, Docker versus LXC, and the advantages of Docker.
Well, if you have Docker versus servlet, I think it would be just in time, you know, we just talk about it. All right, go right ahead. I'm sorry.
What is Docker? Docker is a development tool that makes it much easier for developers to create new applications and ship their application as a singular package. Docker makes use of Linux containers to allow the containment of resources and dependencies of the application, such as libraries. This allows the application to run on any Linux machine regardless of customizations. So pretty much you have your application packaged up in a way that regardless of how their machine is configured, any external resources they have applied, it runs, they'll get the same output as you regardless. This is a little bit of history of Docker. I apologize for the low resolution. In 2004, Solaris containers and the zones technology is introduced. So that's the very beginning of the containers technology. In 2008, Linux containers, or LXC, is introduced, which uses virtual machines and that is what people used previously before Docker. In 2013, Solomon Hykes starts Docker as an internal project within .cloud. In March 2013, Docker is released to open source. And in February 2016, Docker introduces the first commercial product, now called Docker Enterprise Edition. And today, open source community includes 3,300 plus contributors, 43,000 plus stars, and 12,000 plus forks. How Docker works. Docker uses a container system that allows for different parts of an application to be divided into various containers to be called upon as needed. The containers used in Docker are sets of one or more processes that are isolated from the rest of the system. This allows for portability, scalability, and stability. Containers. Containers are the execution environment for Docker. You can package your applications in a container and then proceed to build more containers out from that container. Two or more containers can be linked together to form a tiered application architecture. They can be given commands just like a standard program. Containers versus virtual machines. Virtual machines are similar to containers in that they can run applications in an isolated manner. However, virtual machines lack the portability and expandability of containers. Containers require a few resources to run, and multiple containers can run inside of a virtual machine. Containers can be created and resized at a moment's notice, while a virtual machine may take a while to edit. Docker versus LXC. Docker is a lightweight virtualization solution to run processes in isolation. It has general improvements over LXC. It uses LXC, CS groups, and the Linux kernel itself, and relies on the operating system's own functionality, rather than the host's operating system. Or no, it uses the host operating system, and not a virtual machine. Linux containers. OS-level virtualization technology that allows creation and running of multiple isolated Linux virtual environments on a single control host. It runs the Linux virtual operating system and relies on that functionality. Docker's advantages over LXC. It has portable deployment across machines, versioning, including tracking successive versions of a container, component reuse. Docker allows the containers to be reused and built off of. Shared libraries. Docker has an active community that is constantly contributing containers to other developers. Docker superiority. While LXC offers the advantage of a virtual environment on Linux, such as isolating processes and programs from one another, Docker is clearly superior. Docker allows the easy creation, transfer, and replication of packages, and almost entirely negates the advantages of virtual machines over virtual environments due to its efficiency. Conclusion. Docker is a revolutionary tool to the application development world and will continue to grow and evolve. It is so great for the community due to the collaboration involved. The versatility and efficiency of Docker make it an essential tool in any developer's toolkit. Then I have my citations.
Anyone has any question? Evan, can you remind me again, what's LXC again? Can you go into a little more detail, LXC?
LXC is a similar container-like program that uses virtual environments, or virtual machines rather, to,
So LXC is the Linux container, right?
Yes.
Okay, all right. Yeah, I have not been aware of, in the past, this is probably, the start past few years back, but it's a nice contrast or comparison that you have here. The only suggestion that I would provide, in the future, not just for you, for everyone, I think there are so much text within one slide. Sometimes you may just have only the headline or whatever the bullet list, and then maybe a little more visual or picture or diagram showing something. So then it will make your presentation is more appealing and also not distracting, because one, you have a lot of text and specifically something that I'm not aware of, then I keep reading yours and then don't pay attention to your talk. And sometimes, people are not fast enough that can have a multi-spectrum in terms of perception, right? So I would suggest that any presentation, once you start having a lot of text, I know that those text important, but you can speak it out and only highlight, you know, the headline or the highlight of the idea that you want to tell the story, and then maybe add with some diagram or picture, because picture tell 1,000 words. Okay, so in that case, your storytelling is very, I think it would be more effective, in my personal opinion. Even though I don't speak perfect English, but I think a lot of time, I don't know, I got picked by the company or whatever the team that go presenting. Maybe because I do my homework first, and then I prepare my presentation or communication. Okay.
Yes, sir.
All right, I think it's pretty good information, something that I'm not aware of, so that's why I got appreciate. And I mean the LXC kind of elude for me, and then when you point back to that slide, then I see you already have there. But you know, the point is that if something important, then you may dedicate one slide and talk about it, and then you can move on, because you refer to LXC so much, and then one of the slides you have it there, but it's all text. That sometimes when people busy reading, I was reading on the left hand side, I have not finished parsing or understand the whole thing, then you move on to the next. That's what, you know, I'm trying to give you. I think the content wise, I like it. The presentation a little more kind of, you can improve. I'm not pick on you, but I'm just trying to give my feedback so that everyone learn how to be an effective presenter, because it's equally important, you know, in the future when you start working in the real world. If you are a good communicator, you can excel your career, you can move up so quickly, and then you can, you know, sell your product or tell your story is more powerful, you know. So all right, okay. Anything else, guys, to ask Kevin? Otherwise, Evan, sorry. Otherwise, let's move to the next person. Next person is Jacob Matthew. I'm so sorry that I think I misspelled it. It should be Jacob, not Jacob. Jacob here. Quietness. All right, then let's move to the next person, Isaac.
Hello. Hello.
Yes, I can
All
hear.
right.
Yeah, go ahead and share your screen, and then I will mute after you share your screen.
Okay. 1 second. So my presentation is on virtualization. The history of virtualization. Virtualization originated in the IBM project in 1964, but it was prolonged. The
Hey,
development was prolonged.
Isaac,
Sir,
are you skipping the first, second slides? I think you just show us the first slide.
you don't see the second one?
I mean, right now I see the first slides, but I thought that, do you want to skip the first and second slides?
You want me to?
Well, it's up to you. I mean, if whatever you think that is most effective presentation, it's all up to you. I'm just kind of remind you. But if you think that this is the good start, go ahead, go right ahead.
Okay. What is virtualization? Virtualization is the process of running a virtual mode on a computer system in a layer that comes from the actual hardware. It runs simultaneously, runs multiple operating systems on a computer screen. The general structure of virtualization is in layers. You have the access layer, which that allows the device to run to have any access to any application without knowing too much about it. You have the application layer. You have the process layer. You have the storage layer, you have the network layer, and you have the management layer.
Isaac, do you want to move to the next slide? It seemed like your screen either frozen or you didn't move to the next slide, because
Really?
I kind of see like the next slide is like multiple layers or something. I don't know. I'm just guessing. Just try to help out.
Okay. I always say my screen paused. Now you see? You see it now?
Yep.
Okay.
Yes. Right now it's show.
Oh, it's show now?
Yes.
Okay, my bad. The operating system of virtualization is the main IT.
Hey, Isaac,
Sir.
let's speak on the first slide again because it's important. It didn't show, so let's reset and start from the first slide again.
Okay. Virtualization. That was my topic. And we all know the history of virtualization. It originated as an IBM project, but it was prolonged. And the development of virtualization had entered a stage in a rapid outbreak since Microsoft joined Intel and AMD. What is virtualization? Virtualization is the process of running a virtual remote on a computer system. It simultaneously runs multiple operating systems on a computer screen. The general structure of virtualization is in layers. You have the access layer, which allows you to access the application without knowing. You have the application layer, which allows the application to run in different operating systems. You have the process layer, which does not show the hardware configuration from the operating system. You have the storage layer, you have the network layer, you have the management layer. The operating system virtualization is the main component of the IT infrastructure of the operating system. The operating system may have a compatibility to allow and deny access to such resources based on which the program requests them and the user account and the context which it runs. The application of virtualization is the running application on a machine that does not have apps installed. Applications from the hardware have many advantages, one which is maintaining a standard cost-effective operating system, configuration across multiple machines by isolating applications from their local operating system. And here are some applications of virtualization. You have Parallels Remote Server, you have Citrix Virtual Apps and Desktops, formerly known as Xan Desktops. You have VMware VNapp. You have desktop containers. Virtualization tools are tools that virtualization tools are the topic of research. Virtualization tools support application by testing and imitating components. It creates a virtual effort to test and allows applications to be tested at speed. And here are some virtualization tools. You have virtual network user mode Linux. You have VirtualBox. You have VMware server. You have Qumu. You have Xan. You have VMware. And that's my works cited page.
Okay,
Hello?
all right. Anyone has any question? Well, again, I think the last few presentation, virtualization, cloud computing, Docker, and all those, they are related. I think all, you know, before cloud computing start, virtualization, in fact, is the first concept that being introduced, you know, and then therefore later on people start implement this virtualization, start with virtual storage, virtual server, and then start become, you know, like instead of you have physical hardware, then you have virtual hardware that you can deploy operating system on the top. And then later on, some concepts such as, you know, container, that even further this virtualization, virtual machine, virtual storage in more easier way to manage. Okay, and then, you know, you have this Kubernetes that I think one of our colleagues has presented there. Okay, so yeah, so some of these I think you should put in your radar, and you know, and in that, therefore I think it would be helpful for your future career. Okay, all right, so let's get to the next person if no one has question. And quick thing, Isaac, I think you have too much text. A lot of time you need to mix between text and also cut down some text, because don't just put everything that you're going to present on one screen. Put just like, you know, the main idea or the highlight of the idea that you want to tell, you know, I mean, your story, and then link to the idea, picture or diagram, so that it would make your storytelling more easier to follow and understand, you know, because otherwise people keep reading and then distract, I mean, the presentation or the main thing that you want to do. Okay.
Oh, okay.
All right.
Thank you.
Next one is Amani. Amani, I think it's also another important topic on GPU.
Yeah, I'm here. Let me open it real quick.
Yeah, go ahead. And before I mute my microphone.
Okay, can you guys see?
Yes, go right ahead, Amani.
Okay. My topic is on GPU runtime and OS. Right, so what is GPU? GPU is the general purpose computing on graphics processing units. It is not the same as GPU. It's more of like, it's like the idea that builds a GPU. It's not the actual thing itself. And it helps with some of the harder tasks that the CPU has to do. So the CPU has to like run a little bit less. So the history of GPU. The first GPU dates back all the way to 1978, when Nick Elland and Mary Whitten founded the Iconus graphic system. And the GPU has really started to show between 1999 and 2001, where the GeForce 256, the first ever GPU, was made. And that's that thing to the right. It's very different from like the current ones where you see like the big fans. Well, this thing just has like a small, tiny fan, and the outputs are totally different, and how big the PCIe slots are is just like very different from what it was back then. That just shows like how the idea of how a GPU was made is like completely different, or like slightly altered, I should say.
Yeah, I think in early 2000, you don't have PCI Express, whatever the current PCI Express architecture. I think you have whatever those system bus, which is 16 or 32 bit, which I forgot, but it looked very kind of similar that when I was during the time that, you know, I put all computer by myself. Okay, all right, go right ahead.
So the current state of GPU. The current state of GPU is NVIDIA's CUDA system and AMD's OpenCL. CUDA stands for the Compute Unified Device Architecture. And both use similar programming languages in like C, C++ maybe, and yeah. So some of the competing companies. So like the two biggest companies obviously are NVIDIA and AMD. But there are other ones such as like Asus, Gigabyte, EVGA, Zotac, just to name a few. And you can see like their logos right there. AMD kind of like the up and rising one, while NVIDIA is still just always up there, but AMD starting to catch up, and every other brand is just kind of like a little bit less, I would say. So the positives of GPGPU. The benefits to GPGPU over CPU is that it can like way more double or even quadruple the work that you can do. So like if you have, so let's say you're like a graphics designer, right? If you have like a GPGPU, it makes it like way easier for you to do like multiple layers without having like so much like decrease in system performance. And another positive thing is that you can have multiple of these GPU slots on your motherboard, so that like you can have even more tasks running at once in case you're doing like a very, very big like workload on that day. But the negatives is that the GPU starts slower and ends slower. It also communicates slower to the GPU than the CPU. So like the time between each of them can be like slower as it goes on. That made sense.
Why is negative? Amani? Because I don't see it's negative. You know, I mean, it's just by design.
It's negative because like, it's negative because if a GPU starts slower, so like when you like boot up the system, if the GPU kind of like starts slower, since the motherboard itself kind of like
Are you sure?
I'm trying to think.
You don't need to know. You don't need to. I mean, if you're not sure, don't try to answer.
Okay.
You know, I mean, you can say I can do research, because I've been on GPU probably past 10 years, even though I have not start from like, you know, the first GPU 2000, but I start GPU probably 2008, 2009. And,
Okay.
and you know, the GPU, I think I can see that the negative, if you don't make use of the GPU correctly or smartly, because the way GPU and CPU work together, GPU cannot work by itself. It has to work in junction of CPU. So it's called host and then computing device. Most GPU would call computing device that you just attach as whatever the peripheral, like you just show the card from whatever the second slide there. The current GPU does not look much different than whatever you show there, but you know, the bandwidth or the slot probably larger. And right now, some of the card, in fact, the regular graphic card and GPU, it could be the same. You know, it's just the way to use it. Instead of you display the graphic, you know, like the animation or whatnot, you turn the graphic card to be computing machine, meaning that if you can map your general application into pixel processing. For example, let's say that if you want to do drug design, you know, the drug design is based on molecular dynamics, kind of, you know, like foundation knowledge. And you have a lot of atom or molecule interact to each other. So in that case, if you are mapping those molecular kind of structure, which could be like 10,000 or million of those structure. So in that case, you can represent in, for example, two-dimensional matrix or 3D metric. And then after that, you use CUDA or OpenCL to start represent those data structure and perform data parallel operations, such as, you know, if you want to do matrix multiplication, matrix inverse, FFT operation or whatnot, instead of you do one instruction with one data at a time. Then with GPU, you can do 10,000 or many all at the same time. That's what how GPU works, and it's gonna be, you know, I mean, it's gonna be a main computing power that make some useful application to be even more useful. You know, in fact, AI, I mean, if some of you guys have taken class with me, AI, I think I know very best only half, meaning in terms of computing, because my background is in high performance or supercomputing or GPU computing. And in that case, you know, the only Achilles heel or the negativity of the GPU is the round trip data, because you have to transmit the data from CPU memory to GPU memory, and then you start executing something on GPU in hope that you're gonna speed up the computation. But then if the data transfer from CPU to GPU, and then the result that transfer back from GPU back to CPU, it has a lot more overhead than the speed up that you achieve on GPU. In that case, your GPUs would not be very useful. That's what I would say that is one of the main negativity of, the GPU if someone don't know or don't use the GPU in the right way. Okay, does it make sense to you? I mean,
yeah, I got that. I got it. Yeah.
Yeah, and then beside that, you know, I mean, I see right now the number one company on GPU is NVIDIA, and in fact, they just bought a company called Mellanox last year that they want to be, they want to conquer the world, meaning that because they have very capable computing that would be much faster. Because when you say that is CPU is faster, maybe based on a instruction within the core. But imagine that how many cores would you have on CPU? The maximum number of cores. You probably have 16 core or 12 cores there, right? And how many cores possible on GPU? Have you looked into some detail, possible number of core on GPU?
No, I did not look into that.
5,000. And then you can have multiple GPU card within multiple GPU within one card. Some card, or you have two GPU cards, two GPU stick into one card. So that means you can have 10,000 core there. So in that case, even though it's slower, maybe like 2 times slower, but number of cores, you have like 1,000 more. So in that case, if you know how to use the right way, then the GPU would be very effective computing. That's why AI came back in the past 10 years because of, I can say that because of GPU. Without GPU, AI would not be AI today. All right. Yes. Does it make sense to you?
Yeah.
Okay. All right. So this is important topic as well. I was looking forward to see more from this Amani, but at least, I mean, can you go through the references? Yeah. Here are some references that you can take a look, but also you can go and look at, you know, the current announcement from NVIDIA. In fact, NVIDIA just have a virtual meeting the other day that I think it's very interesting. I would send you the link, the keynote speech from the CEO of NVIDIA from his home. You know, I think it's quite interesting. A lot of marketing kind of wording that, you know, sometimes you need to be cautious, but also there are some merit in terms of, you know, I mean, things coming on the horizon, you know, things that I think you need to be aware of before you graduate. Okay. All right. So let's see. I have one person that asked me an excuse that she want to present next time, but let me ask, anyone has not do any presentation? Please speak up, okay? Because this is your last chance, or next week is your last chance. Not next week. Next class is your last chance, okay? If anyone has not present at all, quiet. Okay. Well, in that case, let's call, you know, I mean, the class off today at this point, and then let's do a quick meeting on Thursday. Okay, I hope that there's a few people who has not present, then they will present the last class, and then I gonna make, I plan to summarize the whole class. And I also will prepare maybe additional or bonus materials, you know, in case that if some of the person, some person who has not present decide don't want to present or want to have your score toward your grade or final grade, then I cannot force. But, you know, I think if anyone has not done or complete any activities such as the quiz or the homework, please contact me as soon as possible. If I see some good reason, then I would open up some of the quiz or the final exam, because I know that I think this time, even though I already give some deadline, but some of us may face some challenge time with the COVID, whether taking care of the family or whatnot. So let's communicate, okay? Because I want everyone to do well. I want everyone to, you know, I mean, got some good grades. So let's speak, okay? So why don't we do this? Let's resume our last class this Thursday. And then after that, you know, I would wish you to have a good summer, and hopefully that will come back to normal or new normal soon. All right, guys. So that's it. Have a good day, and I'll see you this coming Thursday. All right. Have a good day, guys.